Okay, Bismillahirrahmanirrahim. Um, and let us revise a bit of 2D Fourier transform. Uh, so, Fourier transform. We've actually gone through the whole mathematics in detail in the class, but just for a revision, I'll give you the equations first. So, Fourier transform of a signal is given by x omega 1, or let's say w1 and w2. So this is 2D Fourier transform. It is defined as summation n1 going from minus infinity to plus infinity, summation n2 going from minus infinity to plus infinity, of what? Of a signal which was defined over space, and the space is currently 2D space defined over n1 and n2, and multiplied by the exponentials e power minus j w1 n1, e power minus j w2 n2, n1 n1. So these are all the samples, and n2 n2, these are all the samples in the second dimension. So it is a two-dimensional signal. So this is the definition of 2D Fourier transform. So this side, this is a continuous signal. And what was inverse Fourier transform? So inverse Fourier transform was defined as, so what are we getting? We are getting the original signal back, which is small x n1 over n2, which was defined over space, which is equals to double integral from minus pi to pi, and then minus pi to pi. Double integral of what? Double integral of the Fourier transform of the original signal, which is defined as, which is this one, x defined over w1 and w2, multiplied by e power j omega 1 and 1 and e power j omega 2 and 2. So the integral here means that we have to have d omega 1 here and d omega 2 here. So there needs to be a scaling factor. So there is double integral over 2 pi each, so we'll have 1 over 4 pi square. So this is where we have this is our discrete signal, and gives us a 2D continuous signal. We have the 2D continuous signal here, 2D continuous signal in Fourier domain, and we get our original 2D discrete signal back. So now let us look at some examples of the 2D signal and related to sampling. Okay, so this is again a part of lecture which we had covered in the class in detail, which was 2D sampling. We actually had a look at 1D sampling and all the associated knowledge that we need to know regarding 1D sampling, and then we extended it to 2D sampling because we're going to do it in terms of image processing. So let's concentrate on 2D sampling for revision. So let's say we have an image, and let's say I'll try to draw an image. So the image is something like this. I think I did the same in the class where I draw a Mercedes Benz, let's say a cheap one, and we sample this image. So what we are assuming is that the image is actually continuous, so it is not captured by your digital camera but actually captured by some old camera, and then we try to digitize it, so we are sampling it. Now it is defined over space, so we are sampling over space. So there is this width, let's say t1, and then this other width t2. So when we covered the 1D sampling part, I had discussed it in detail. I'm not going to go into much detail here because I want to go to next topics. But we can have the 2D Fourier transform of the original 2D signal, which is drawn in black, not the sample version. And the support of that signal is going to be somewhere around here. So this is not the the shape is not the 2D Fourier transform of the image, but it is actually the area where all the frequencies are present, those frequencies which are actually present in the image. So this is the support which I have drawn here. We had covered this in detail in the class. And let's say the axis is not W1 and W2. Let's say W is defined as omega into T. So let's say omega W1 is equal to omega 1 T1, where W1 is in radians. So these are all the frequencies. Omega 1 is in radians per millimeter over space. So any unit can be used. I'm using millimeter, which means T1 is in millimeter. So these are samples in space. So if my axes are this omega 1 and omega 2, then the signal that I've drawn here is the Fourier transform of the original image, xa omega 1 and omega 2. But if I draw the Fourier transform of the sampled image, then I know that I'm going to get not just this, but copies of it repeated after every 2 pi. Here, if the axis is omega 1, then the copies are actually repeated after every 2 pi over T1. So I'll use a different color for the copies. So let's say this is 2 pi over T1. This would have been 2 pi if it was W1 and W2. This would have been 2 pi here as well. But because we are using omega 1, so it is 2 pi in radians divided by T1. So not difficult, I hope. So the signal, I'm again drawing the support of the signal. So because the actual signal strength is in 3D, which is coming out of the board, right? Again, we had covered this in detail, so I'm just revising it so that we get used to online lectures. So it is here as well, and we have it here as well, and not just here, actually we have multiple copies here. This is 2 pi here as well, here and here, and this basically goes on, it doesn't stop. And the equation that governs this transform is x of, so this is W1, but now I'm using omega 1 T1. So this is a Fourier transform 2D, omega 2 T2, which is equals to 1 over T1 T2. Again, this scaling periods which are getting multiplied, and then divided, uh, they are getting divided over summation of all the samples that we have, because now it is the signal that we're using is not the continuous signal, it is the discretized version of the original signal. So we have in total k samples in one direction, let's say k1, and k2 samples in the other direction. So we have k1 samples here, k2 samples here, and then the transform is given by xa. I think I should use small. Okay, this is not small, it is actually capital XA. I'll tell you what it is. Repeated over after every 2 pi by t1. So this is omega 1 minus 2 pi over t1 k1, and omega 2 minus 2 pi over t2 k2. So what is this? So, the x that we have written is the 2D Fourier transform of the discretized version of our input, where XA, capital XA, is the Fourier transform of the continuous input. So this is this blue part, and when we repeat this blue part after every 2 pi by t1, and this goes on basically for all omega 1 and for all omega 2, then the signal that we get is this, and this is actually multiple copies of the original Fourier 2D Fourier transform. So this blue part is one single XA, which I have written here. Let's say for k1 equals to 0, we get XA omega 1 omega 2. So this is XA omega 1 omega 2, only this one. And capital X omega 1 t1 omega 2 t2 is the discretized version, which is accumulating all of these together. So this is the 2D Fourier transform of the discretized sampled version of our image. Now we had discussed multiple type of sampling. So we had discussed critically sampled, we discussed oversampled, and then we discussed is it visible? I think it is. No, it's not. So and then we discussed undersampled. And we know that the Nyquist criteria dictates that the sampling frequency should be greater than or equal to the double of the maximum frequency contained in the signal, in the input signal. So critically sampled is when this criteria is just met, which is sampling frequency is double of maximum frequency. Oversampled is when it is greater than, megahertz is greater than double the frequency. Undersampled is when megahertz is less than 2 omega m, and this means what? This means that we're going to get aliasing in the signal, in the 2D Fourier signal. Okay, so again, we had covered all of it in detail in the class, but I wanted to do a quick revision so that when we go forward, we have sort of a refresher in the online classes. Okay, see you in the next lecture.